Hello everyone, I welcome you all in this lecture. So in this lecture we are going to study how the aircraft perform the takeoffs. Okay, so this is a typical picture you can see here. This is the aircraft which is at, you can say, rest V0. Okay, Vs is the stall speed. Okay, minimum speed at which you can sustain a level flight. Okay, very important speed. Okay, below the speed aircraft will not able to fly and you cannot sustain a level flight below that stall speed. V1 is a critical power failure speed or decision speed. If you cross V1 and if one engine is fail, or I mean to say, is there any kind of engine problem, you have to take off and then again land. Okay, because below the V1 speed you can actually take a decision and you can stop the airplane, but when you cross V1 you cannot do that. Okay, VR is a rotation speed. When you reach at this speed you will put the elevator up so that you can rotate and you can achieve the lift off speed. Okay, and V2 is a climb speed which is 20% more than the stall speed, and V lift off speed is a 10% more than the stall speed. So stall speed is a reference. Okay, 10% if you take more you will get lift off, and 1.2 might mean to 20% you will get more, you will get the critical speed. Okay, and this is called obstruction height, generally 10.7 meter, because when you take off from any runway, as you cross the runway there will be buildings, trees and all, so in order to keep in that mind you have to take this height. Okay, for a safety side. Okay, now just take some common aircraft, commercial aircraft, and have a feel for what kind of takeoff speed we will get. Okay, so now we have taken the example of a A320, Airbus 320. So you can see the weight is around 75,000 kg and wing area is 123. Since we are taking a takeoff at a sea level, so sea level density is 1.2256 kg per meter cube, and CLmax is 2. CLmax is 2 with flap deflection. So I already explained to you, flap is the control surface. You can see this, when you deflect it will change the camber and will increase the lift. Okay, we'll see what is the significance, why we generally want this increment in CL. Okay, so 2 CLmax, then you will get the speed around 70 meter per second. If you multiply by 1.9438, that is nothing but the conversion factor from meter per second to knots, you will get 136 knots, and the climb speed you will get will equal to 1.2 into 136, that is 163 knots. Okay, so lift off, you can see the climb speed is 163 knots. Okay, and stall speed 136 knots. Okay, now many speed are written right here, this minimum control speed. So you can see that there is a just after the Vs you have a minimum control speed. At this speed the control surface starts affecting. Okay, now you cross the stall limit, right? So obviously it will get this will become effective. Okay, 9.81 is acceleration due to gravity, and this we have found out using lift equal to weight. See, this is a Vs stall speed, W is a weight. Okay, rho is all the parameter I have taken. It is also written here. Okay, all right. Okay, this is a rough sketch. You can also see that is a more detail. You can see where you have a takeoff distance and you will start rotating. Okay, and then you will climb, because it is not like that when you take a plane and start moving on the runway and immediately you will climb. You have to rotate the aircraft, right? And first, the how the pilot perform the takeoff, you can actually have a feel when you are about to take off, what you will do, you will put the foot throttle and you monitor the speed, like I said, VS, V1, VMC, every speed you have to monitor. Okay, once you reach that speed, perform the action accordingly. Like when you reach the rotation speed, you have to put the elevator up in order to rotate the aircraft. Okay. Okay. Now you can see here I have listed also SG is a ground roll distance. Now we are interested to find out what is the takeoff distance formula, expression, fundamentals. Okay, we'll go. Okay, so SG is a ground roll distance. Ground roll, that means your wheel is on the ground only. You are not lift the aircraft. Okay, so up to this, and then you will rotate and then start climbing. Okay, so takeoff, taxi, ground roll, then rotation, and then climb. Okay, initial phase of climb, that is also part of the takeoff. Okay, where you should clear the obstacle height. Okay, so here I have also listed V stall speed. Okay, and VMCA, minimum control speed. Okay, minimum control speed on ground, minimum control speed in the air. So here in detailing, I have explained. I'm trying to explain two speed. In the previous slide, I have just said that key minimum control speed, but here there is a two minimum control speed in the ground as well as in the air. Right? VR is a takeoff rotation speed. Okay. And if you clearly observe here, there is a three phases involved, right? Ground roll and then rotation and then initial climb. So you will have a three distances also. If you sum together, you will get the total takeoff distance. Okay, for this point and climb. Okay, and wherever you have a performing the, I mean to say, what you can say, ground roll, and then basically in rotation, what you are doing, you are pulling up the aircraft, and pull up maneuver I already explained to you. So in this, whatever the distance you will get that you can say transition distance or flare distance. So ground roll distance, and then this is a transition distance and flare distance. Okay, and the remaining part will be the initial climb. Okay, so I hope things are clear. Okay, and one more speed I want to explain, VMU, minimum unstick speed. So minimum unstick speed means it is a speed which is little less than the lift off speed. In this speed, actually, even if you rotate the stick, I mean to say up, aircraft will take off, I mean to say. Okay. So as an engineer, how will you write the equations of motion? Because when you write the equations of motion and you do the calculation and all, then finally, or do the derivation and all, then you will find out the takeoff distance. So like that, you write mv dot, v dot is the acceleration, t minus g, t is the forward thrust force, d is the backward drag force, you can see, and minus mu r, w minus l. So mu r is a friction coefficient. Okay, and w minus l, you can actually balance the equation. When you integrate velocity, you will get distance, right? So this is how this integration is written, and finally you are going from 0 to lift off speed or take off speed, right? And when you do this, you will write this expression and you can find out A and B like this. That's the arrangement of this. Okay, so V, by integrating V, you will get the distance. Okay, so you can write this in this integration form, and in order to make this expression simple, you can write A plus BV square, where A and B is written here. Okay, K1 is the induced drag coefficient, A is this expression, V is the takeoff speed, CL CD naught is the lift and parachute drag coefficient, delta is CD naught is a drag increase due to extended landing gear, because when you deploy the landing gear, or when the landing gear is extended during the ground roll, that also will produce the drag. And G is a ground factor, where the 16h by b divided by 1 plus 16h by b whole square is a reduced factor in the induced drag due to the ground effect. Okay, so here h and b are the height from the ground and wing span respectively. Okay, so if you have any doubt regarding the ground rule, I can take a separate session for this ground rule and all, and or if you have any doubt you can put in the comment section. I will explain in detail. Okay, I can attach my research paper also. We have done the autonomous landing with the ground effect. So there you will find the detailed explanation. Okay, but here now in this lecture the purpose is to understand the takeoff. Okay. Now when you take approximation, thrust is much greater than d plus mu or w minus l. Okay, and all the lift, drag, everything computation you can do on a 0.7 into wheel lift off speed. Why 0.7? Because when you are at a ground no speed, and when you are at a stall speed, so in between you have a speed at which the aerodynamic control surface start affecting it. It's not fully functional, but it start lift is start producing, drag is also start producing. Okay, okay. So that average speed, the factor is 0.7 is there. Okay. So when you do this approximation, you will get 1.21 W by S divided by G rho CLmax T by W. So here this is this in this approximation, basically you are neglecting the other two takeoff distances, that means transition or flight distance or and initial climb. So here you can see that the takeoff distance is directly dependent upon the wing loading. When you increase wing loading, takeoff distance will increase, and when you go for a higher and higher altitude, density will drop and takeoff distance will increase. For example, let's say for any kind of aircraft, you have a takeoff distance 1 kilometer at a mean sea level, and when you go for any high altitude region in India, for example like a Leh Ladakh, okay, then the takeoff distance will increase. Here you can see that CLmax dependency. When you increase the CLmax, the takeoff distance will decrease. So as an engineer, we want the reduced takeoff distance. Okay, we actually everywhere we want to reduce the runway length. Okay, so that is why we are doing some kind of engineering here, increasing the CLmax. Okay, decreasing the wing loading, and when you increase the T by W, also the takeoff distance will decrease. That means if you have a more powerful engine, you can actually immediately perform a takeoff, for example. See the dependency. Okay, so you can see that when you design any kind of UAV, small UAV, surveillance UAV, or any general aviation aircraft or any fighter aircraft, so wing loading plays the major important role here. Okay, and depending upon the wing loading and also the thrust loading, T by W is the thrust loading, W by is the wing loading. Okay, so you have to know all the dependency of the parameter. Okay, so this is approximate ground roll distance for a takeoff. Okay, so in the next lecture I will take the landing, but since I have completed that both code part for a takeoff and landing, so I thought it's better to put the graph. You can see I will focus on the takeoff only. You can see um, the takeoff time is almost what you can say 30 second, and total takeoff distance is around I mean to say here ground roll distance is around 500 meter. Okay, so you can ask that how I am getting this 500 number. Basically, uh, when you go for a flight control system design, we have taken an example of sinus glider. So there I have detailed discussion about the aircraft model. The same model we have taken here, and we have done the takeoff calculation. Okay, if you are more interested to know how I have achieved this, and then you can put the comment in the YouTube section. I will try to answer. Okay, so these results correspond to the same aircraft which we have taken in the flight control system design course during the autopilot design. Okay, so we'll meet in the next lecture. Thank you so much.